combination circuit. Now, the first thing you want to do in these is you want to identify which resistors are in series and which ones are in parallel. And then the next thing you're going to do is reduce this down step by step to a 1 resistor circuit. So the first thing is I identify the negative and the positive sides of my battery, and I trace my current path. So the total current is going to split up here, and some of it's going to go into R1 and some of it's going to go into R2. So I know that these are in parallel with each other. I'm going to come back together. It's going to be I here, and then it's going to split up, and some of it's going to go into R3 and some of it's going to go into R4. So R3 and R4 are in parallel with each other, and R1 and R2 are in parallel with each other, and then it meets all back up to be I. So there are definitely different current paths in this circuit. So the first thing I'm going to do is I'm going to simplify this down to a circuit that only has 2 resistors in it. So these two, the 100 and the 250, can be reduced down to 1 equivalent resistance, and the 350 and the 200 can be reduced down to another equivalent resistance. So REQ1 is going to be equal to 1 over 100 plus 1 over 250, and I'm going to take the inverse of that. 100, 1 over, plus 250, 1 over, equals, and then 1 over again, 71.4. And REQ2 is going to be equal to 1 over 350 plus 1 over 200 to the negative 1. 350, 1 over, plus 200, 1 over, equals 1 over that. And I'm getting 127. So this is a 127 ohms, and this is 71.4 ohms. And now these two are acting like one resistor. Okay, and they're simply, I just add those together. 127 plus 71.4 is going to be 4 and 8, 198.4 ohms. Now, let's talk about the current in these. So, I'm going to work backwards. I've got a 24 volt battery attached to 198.4 ohms. I can figure out the current that is going through, the total current that's going through this circuit. I is just going to be the voltage, 24 volts, divided by 198.4 ohms. 24 divided by 198.4, which is 0.121 amps. Okay, so now I know that if I expand this back out, that going through the equivalence is 0.121 amps. I know that the amps that go through this and the amps go through this are 0.121 amps because it's all on this. This is the same loop as that loop. There's no other loops up here. So that means that the voltage for this first equivalence is going to be 71.4 times 0.121 amps. Seventy-one point 4 times 0.121 is 8.64 amps. Excuse me, volts. And for REQ, the voltage across that is going to be 127 times 0.121 amps. 15.4 volts. If I add 8 and 15, I get 23 and 0.6 and 4, so I get 24 volts, right? These two should add up to be, because these are in series, their voltages should add up to be the 24 volts. And there is a little bit of a difference only because of rounding, but yeah, 24 volts. So, what does this tell us? Well, let's make a list. So R1, R2, R3, R4. B equals I, R. So we had a 100, and we had a through 50, and we had a 350 and a 200. 100 and a 250 and a 350 and a 200. What do we know so far? We know that the voltage from this point to this point, this junction to this junction, right here and right here, is 71.4 times 0.121, or 8.64 volts. So we know the voltage is 8.64 volts, and that means that the resistors that are in parallel here have that. We also know that the voltage for the other two resistors is 15.4 volts. Once we know what the voltage is across all these resistors, we can use V equals IR, or I equals V all over R to find the current through each of these.